All right, next we're going to talk about some properties of definite integrals. So if we're looking at this definite integral, the limits of integration are from a to a. And if the upper and lower limits are equal, then the definite integral is going to be equal to 0. In other words, there's not going to be any area in there if we go on the interval from a to a. So when it's the same, it equals 0. Now, in this case, if we reverse the limits of integration, we actually reverse the sign of our integral. So we'll just say that this is the integral from b to a and of f of x dx. And that's going to equal the opposite, or the negative, of the integral from a to b. Okay? So if we switch the limits of integration, then we switch the sign as well. All right, next, the additive interval property. So if we have an interval from a to b, and we have an interval from a to c and then c to b, if we can add both of these up, then we get the interval of the first one. So this one's a little bit easier if we look at a drawing here. So I'm just going to put a little coordinate grid here, and we'll just say that a is right here, and then here is b, and that c lies somewhere in this interval. So we'll just call it right here. Now, if I draw a function that's on this interval, okay, if I want to find the entire definite integral from a to b, I can simply add up my integral here from a to c, and then from c to b. Okay, so we can just add those two intervals together to get the one big interval. Another property is the constant multiple property. So if k is a constant multiplying by your function, you can actually pull that constant outside of your integral. The additive function property says if we have the definite integral of two functions being added together, dx, well, we can actually split those two functions apart and find the definite integral of each one separately and then add them together. Another property is the preservation of sign property. And it says that the definite integral of a function from a to b is going to be greater than or equal to 0, where the function itself is greater than or equal to 0. So if we're looking on an interval here, and we have our function is positive, okay, then I know that the definite integral is also going to be positive. Okay, so the preservation of inequality property states that the definite integral from a to b of f of x is less than the definite integral from a to b of g of x, where f of x is less than g of x. So the functions and their integrals often have the same types of properties, same signs, and then the same inequalities. So let's use the properties here to evaluate some of these integrals. So in this case, we're looking at the definite integral from pi to pi of sine x dx. Okay, well, you'll notice here that this interval is the same, and so this has to equal 0 following this one right here. In our next one, we have the definite integral from 3 to 0 of x plus 2 dx. Now always be careful when your lower limit of integration is actually a bigger number than your upper limit of integration. What this is going to mean is we're actually going to be reversing the sign. Now if we look back, okay, here we have the definite integral from 0 to 3 of x plus 2 dx, and that equals 21 over 2. So let me bring that over. Okay, so we can see here that the only thing that actually switches is the limits of integration. So instead of going from 0 to 3, we're going from 3 to 0, and so what we do with that is we just negate our definite integral. So this would become negative 21 over 2. All right. In our next one, we have the definite integral from -1 to 1 of the absolute value of x with respect to x. So what we want to do here is we're just going to draw a little sketch of what this looks like. So absolute value of x looks like this. We have our vertex there at 0. And if we want to go from -1 all the way up to 1, okay, so this is a geometric shape that we don't understand what to do with. But if we were to split these into two geometric shapes, we could see that we have two triangles here. And so what we're really going to do here is split up this integral using the additive function property. And so we're going to write this is -1 to 0, okay, and then this function right here is -x. And then plus the definite integral from 0 to 1 of this function, which is +x. And we have our dx's in there just so that we can take that definite integral. And if we're looking at this, okay, we know this is a triangle, length of 1 and 1, so 1/2 base times height. That gives me 1/2 here. And then the same thing for this one, 1/2 base times height, so it's 1/2 plus 1/2, or 1. Alright, so there's some basic ways to use these properties of definite integrals to evaluate them. Alright, in our next example it says evaluate the definite integral using the given values. So here we're told that the definite integral from 1 to 3 of x squared dx is 26/3, and that the definite integral from 1 to 3 of x dx equals 4, and the definite integral from 1 to 3 of dx equals 2. And it says go ahead and evaluate this definite integral from 1 to 3 of -x squared plus 4x minus 3 dx. So the first thing that we're going to want to do is separate these out. So we see different terms here of our polynomial. We're going to split into 3 different definite integrals. So this will be -x squared dx, and then plus the definite integral from 1 to 3 of 4x dx, and then plus definite integral from 1 to 3 of -3 of -3 dx. Okay, so once we've split it up, now we can go, that was using the additive function property. Okay, so now that we've split these up, we can go ahead and take out our constant multiples. So this has a negative, so we're going to pull that out right here. And then here we have a 4, so we're going to pull the 4 out. And then here we're going to pull out a -3. So this is the constant multiple property. Now perhaps I should back up a little bit. Remember, we were already told what some of these definite integrals were. So this was just x squared. So when we looked at this function, we wanted to get x squared by itself, and we've done that. Okay, we wanted to get x by itself, and we've done that. And then we wanted to get dx by itself, and we've done that as well. So now we know here this is going to be negative. Well, the definite integral of x squared is 26/3. Okay, and then plus 4 times, well, the definite integral from 1 to 3 of x is 4. So 4 times 4. And then minus 3 times the definite integral from 1 to 3 of dx, which is 2. Okay, and so using that substitution, we can go ahead and figure this out here. So this is -26/3. Okay, this is 16, so we'll multiply that by 3 and get 48/3. and this is negative 6, so we'll multiply that by 3 and we'll get negative 18, so negative 18 thirds. And if we add all this up, we end up with 4 thirds total. And so this right here is the definite integral from 1 to 3 of negative x squared plus 4x minus 3 dx. Alright, in our next example, we want to simplify the definite integral. So notice it doesn't say evaluate. We're just looking to simplify. So now we want to take those properties and see if we can rewrite this as a single definite integral. So we're going to go backwards a little bit and combine these. So here we have from 1 to 10, and then this one picks up from 10 to 12. And notice it is of f of x, so that function is the same. So we went from 1 to 10 and then 10 to 12, and so we know that we can add these together. And so this is going to be from 1 to 12 of f of x dx. Okay. Now sometimes it's going to be helpful to just draw a picture. So here was 1, here was 10, and here's 12. And for f of x, you can just draw any function. It doesn't really matter. So here would be the first definite integral, and here would be the second definite integral. And you can see that we can just add them together, and we're going to get this definite integral right here simplified. All right. In our next one here, let's go ahead and draw our picture first for this one. Okay, so this is from 10 to 2. So 10's over here, and 2's over here. And then this one is from 13 to 10. So 13's over here, and 10's over here. Okay, so we'll just draw our function again. Now, in this one, you have to notice that we're going backwards from 10 to 2, and then backwards from 13 to 10. So really, if we went from 13 to 10 and then 10 to 2, we could rewrite this as going from 13 backwards to 2. And then this is going to be of f of x dx. Now, we usually don't like having the larger limit on the bottom, so we're going to switch this around to finish our simplification. And to do that, we're going to make it negative. So negative definite integral from 2 to 13 of f of x dx. So we like to switch that around going in the correct direction. Now, just as a side note, you could have noticed that this was going backwards in the first place. So instead of going 10 to 2, you could have switched this and gone from 2 to 10 of f of x dx, as long as you make it negative. And you could have done the same thing right here. From 13 to 10, we could have switched that and went 10 to 13 of f of x dx, as long as you made it negative. Then at this point, you could have factored out the negative, so that would have been plus there. Alright, and then you could have seen that it went from 2 to 10 and 10 to 13, so your final answer would have been 2 to 13 of f of x dx. Okay, so whether you took the negative out first and switched the limits, or you just thought about it a little bit differently and then switched the limits, either way, came up with the same answer. Okay, for example C, let's go ahead and draw a picture of what's going on here. Now notice this one's going to be from 6 to 2, so here's a 6, and then here's a 2 of f of x. Okay, so that's going to look like that. Oh, and notice the direction here. It's going backwards, giving us that negative number. And then the next one goes from negative 4 to 6. So here's negative 4 to 6. So I'm going to draw f of x. Okay, And so negative 4 to 6 is going to go all the way from here on over. So what this has the effect of doing, it adds up all this area from negative 4 to 6, and then it backtracks and subtracts it all the way from 6 to 2. And what we're left with then is the actual area being right in here. Okay, you guys see that? So we went from negative 4 to 6 and then backwards from 6 to 2, and so all of this is just like going from negative 4 to 2 of f of x dx. Alright, so a little bit tricky there, but hopefully you can see this visually what's happening. Now, another way to think about this is we can change these limits of integration around. So we could have rewritten this as being from 2 to 6. That would change our sign. And then that would be of f of x dx. And then this here would be from negative 4 to 6 of f of x dx. And that's added together. Now, if we switch this around, we can see this a little more clearly. So it would have been negative 4 to 6 f of x dx, which is the second definite integral, and then it would be minus the integral from 2 to 6 of f of x dx. So again, you can see we're going all the way from 4 to 6 of our function, but then we're subtracting everything from 2 to 6. And so that is going to leave us with negative 4 to 2 of f of x dx. So it's just a more numerical way of looking at this, but either way we come up with the same answer. Alright, so that is properties of definite integrals and how to evaluate definite integrals using them, and also how to simplify definite integrals using the properties.